Okay, so here we are. We're going to talk a little bit about uncertainty and error. It's a little beyond what we've done thus far in our course, although it's very related to what we've done. And so here's how we're going to do it. We're going to focus on lab 3.1. This was acceleration around my house, and we focused on the drop problem. Okay, so what we have previously called sources of error, we are actually going to quantify today. And in quantifying them, it makes sense to actually call them by another name, which is sources of uncertainty. And we can actually go ahead and quantify our uncertainty. So that's where we're going to go with this today. We also have something called our percent error. And percent error, you know how to solve. Percent error equation was you take your measured value minus the accepted value over the accepted value or magnitude times 100. In the case of this lab, what we are going to use is our acceleration accepted is 9.8, 2 sig figs, meters per second squared. On your reference table, it says 9.81. Here we're going to do 9.8. Okay, so 9.8 meters per second squared, and this is because it varies by location a bit. 9.81 Eastchester we looked up is more like 9.80, so let's just stick with 9.8. Now, you had a measured acceleration that you determined. Acceleration measured equals. And there was a range of magnitudes here. You might have had anything as low as, well, some people are even lower, but I'll throw in, let's say, 8.0 meters per second squared, maybe up to like 11.6 meters per second squared. Some people are less, some people are more. But the question is, let's pick something in here. Let's say you got 8.7 meters per second squared. This is just a sample. This is not your magnitude. Let's say you got that. Now, to determine your percent error, that's a pretty easy process. Percent error. And it is, you take your 8.7 meter per second squared minus the 9.8 meter per second squared over 9.8 meter per second squared times 100, and you get your percent. So your percent error in this case, let's see, that's negative 1.1 over 10, and that would be negative 0.11 roughly. This is almost 10. Negative 0.1 times 100 would be about, this one would be about a negative 11%, roughly speaking. Okay, the question though, does this, let's see, deny the PRT1 result of 9.8 meters per second squared? Basically, does the experiment that you did, is it, when they say within error, is it possible that 9.8 is legitimate? Because we're looking to confirm what we see on the reference table. Should we just accept that number, that 9.8, or is that actually something we can see ourselves at home? And you can't answer this question until you quantify your error. And we can do that with this process called sources of uncertainty. So we had an equation. As it turned out, our equation was based on our givens. Our givens, we assumed the initial velocity, you measured the distance, you measured the time, and we found our acceleration. And so the equation that went with this, d equals VIT plus 1/2 AT squared, this equation actually guides us to where uncertainty can enter our measurements in terms of finding acceleration. So acceleration here, if we rearrange this equation, it becomes acceleration equals, if you subtract VIT from both sides, d minus VIT over, divided by the 1/2 t squared. This is acceleration in terms of, really, if we want to put properly our hats, displacement, initial velocity, and time. And so error can enter via displacement, time, and initial velocity. Those three places is the only where uncertainty can come in, because anything else that changes has nothing to do with this. Change the ball color. It's not in the equation. It doesn't matter. Change the ball mass. It's not in the equation. It doesn't matter. So based on the experiment we did, these three are what we need to focus on. And that's what we're going to do right now. I'm going to help you out with that. It's not an easy process, but it actually is a very helpful process for thinking. So let's say here, we're going to look at the uncertainty in the displacement for the drop. We're going to look at the uncertainty in the time for the drop. And we're finally going to look at the uncertainty in the initial velocity of the drop. That one really is an assumption we made, but we have to think about whether it was a legitimate assumption. So how do we actually go about doing this? Well, let's check this out. We're going to make up some numbers here to give you a sample. What you're going to put here, in order to find the uncertainty, you're going to put exactly what you got. So let's say this student, I'm going to pull up a video. Where's that video? Here we go. I'm going to pull up a video. Now, this video is one we looked at in class, and this is a pretty good video. Good, real simple. Boom. So let's say that this student measured from the deck surface up to, well, it's a little tough here. You see, there's like a starting point, obviously, but where is it exactly? Did the student have it marked exactly on the window here? Perhaps they had measured to the bottom of the sash here, and their arm was a little below it. There's a number of possibilities. Did the ball stay exactly as it was supposed to at the beginning of the drop? Really, you want the bottom of the ball measured down to the surface that it hits. Even the surface it hits could be a little uneven. So the question here, how much uncertainty is there in the measurement of this height, of this distance? Now, this depends on your situation. I don't actually know what measurement device this student used to figure this out. If you use something fairly accurate, like a spring-loaded tape measure or perhaps meter sticks, you can get things down to the nearest, well, 1/16 of an inch if you did inches, or millimeter if you did, and you even get a rounding digit if you did your meter sticks. But it's possible here, just for the sake of argument, that this student could have moved their hand either easily 5 centimeters up or down. 5 centimeters is not a big distance. 5 centimeters up or down. You even get a little uncertainty on the ground here. So perhaps we'll give an estimate here of 5 centimeters of uncertainty. And so how does that play out? As follows. So let's say that student measured that distance to be. I'm going to make up a number here. Let's say that student measured the distance to be 2.1 meters. Again, that's someone's made up numbers. Now, what you can add to this is the uncertainty, plus or minus. Based on that student's video and our assumptions about how they filmed, maybe they could have been off by as much as 5 centimeters. Some of you will find you were very careful, had your arm pressed. Maybe you think your uncertainty is a little less. No one is zero. Get that out right away. No one is zero. Maybe you're even more. In fact, there's a good likelihood if you're dropping from way up and the tape measure, maybe it reached right. Maybe you didn't think about the width of the tape measure itself. Maybe the tape measure was floppy, whatever it was. Easily you could have 5 centimeters or 0.05 meters of uncertainty in that drop measurement. Okay, fine. So there it is for that drop. You have to think about your own. How about now for the time? What uncertainty is there in the time? Well, let's pull that video back up and see. This video in particular is 60 frames per second. And so I'm going to try to pull along here, and this goes frame by frame. Frame, 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 frame. Now, one of the spots that's difficult to get is actually when the drop truly occurs. Because the ball is dropped, that actually means it starts out at 0. You can't judge by motion. It shouldn't be moving when it's dropped. So if I'm looking at the fingers right here, one thing I see, there, I see the fingers move, but I don't think it's released yet. I see them move again. Maybe that's the release point. Even once more. So is it here? Is it here? Is it here? You know what? It could even be one beyond that, but I'm going to say that it was here, and I'm going to say plus or minus 1 frame. I'm not sure if it's 1 frame before or 1 frame after. I'll choose this one, and I'll say plus or minus. So this is frame 0. Now I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let me pause for a second. There were 2 frames already that I saw that it looked like it kind of jumped. And that to me says error with the video. But let's keep going. 16, 17, 18, 19, 20, 21, 22. Look, right there it seemed to jump. There's 21. There's 20. Look, 20, 21, small, 22. That's a big jump. There's something funky is going on in the video. 23, 24, 25, 26, 27, 28. That would even look like a jump. 29, 30, 31, 32. And I don't know if it's hit yet. 33. Let me go back. 32. And then 33 only moves a little bit. So 32, 31, big gap. 32, and then 33, a little move. There's something's not right there. I'd say 32, maybe 0.2, because now it's on the way back up. So I could definitely be off by a frame at the bottom. So I'm going to say 32.2 frames. And there were other complications here. So let's check this out. I'm saying that mine was, I'm going to do a little math now here, 32.2 frames. So we can turn that into seconds, by the way. So frames, seconds. This one was 60 frames per second. And, well, do a calculator. 32.2 divided by 60. So this is about 0.54 seconds. We probably cannot do better than 2 sig figs here. So I'll come up here and say, I think that my best guess at my time is 0.54 seconds. But you got a plus or minus. There was 1 frame at the beginning that it could have gone either way. There was 1 frame at the end that it could have gone either way, or that we can't quite tell where it is. So that's 2 frames already. And then, on top of that, there were 4 separate times, if you really follow it carefully, there were 4 separate times in the video that it looked like the video jumped. Now, does that mean I lost a frame? Did it jump because the video skipped a frame? Like maybe there should have been then 4 more frames in there. So that all of a sudden brings a whole new level. And really, if you want to do this carefully, you go back and look at your video again and look at your video again and really try to count it. So maybe I'm off 1 at the beginning, 1 at the end, then possibly 4 were skipped in the middle. That's plus or minus 6 possible frames. And if we do our 60 frame rate, 60 per second, boom, boom, 6 divided by 60 is 1 divided by 10 is 0.1. I could be off by as much as 0.10 seconds. Huh. Now, some people just threw numbers out here. I saw some of you tried this, and a valiant effort. I appreciate it. However, you're not going to be off by half second. That's almost the entire time. Don't just guess. Actually count. If your video doesn't have those funny jumps in the middle, maybe you didn't miss any frames. But you will have some uncertainty at the beginning, and you will have some uncertainty at the end. Okay. Now, let's come down over here. The VI, was the VI 0? Well, we certainly hope, that was our intention, that the VI is 0 meters per second, plus or minus. But the reality is, it's very hard to truly drop something. Well, that's it, to truly drop something by hand. Part of the reason is, if we back up here, if you watch even this student, as soon as you let go, your hand rebounds up a little bit. And so the question was, as your hand rebounded up, just a pinch, did your thumb still touch the ball slightly? Did it give it a little bit of a pull upward? Or even better, or more likely perhaps, is as you were going to position to drop it mentally, you're kind of like, I need to drop it. So you sort of give it an ever so slight push downward. It's possible. This student looked to do a pretty good job, but there's possible a little bit of initial velocity in there. And so this one is going to be very hard for you to estimate. So I figured I'd throw a rough estimate out there for everyone just to use on this one. Unless in your video it's obvious. So I would say in your video, if it's non-obvious, I estimated something like maybe you would move as much as 4 centimeters in a frame, or in, probably one frame. So what does that give us? 0.04 in maybe it's 2 frames in a 60. That would give you something like 0.04, 30. Okay, that give you an initial velocity of, let's say, about plus or minus 1.2 meters per second. If it's obvious, however, if you look at it and you're like, whoa, I can see I pushed or pulled that thing a little bit, you better make it more than this. You better make it greater than 1.2. So I'm going to come over here and I'm going to say 1.2 meters per second. Okay. Now, this allows you to come up with 3 different pieces of uncertainty. And these pieces matter. Now, I'm going to give you a kind of a cheap and easy way to get this, and then I'm going to make a second video that's a little more complex. So it's up to you. If you want to do, cheap and easy is the wrong phrase, but if you want to do more of what we call, let's say, the brute force method on figuring out the legitimacy of what you see here, here's what you do. You take your equation. Your equation is A equals D minus VIT and so on. So A equals D minus VIT over 1/2 AT squared. So here's the first thing you do. Make acceleration as small as you possibly can. A minimum. And let's see what happens. So minimally, you would take your smallest, you want the numerator to be small. So you take your smallest possible displacement, which would be 2.1 minus 0.05. Let's put another sig thing on this, otherwise subtracting doesn't really make sense. Minus, so you would have 2.05 minus, now you want VIT to be as big as possible. So take VI as, let's see, 1.2, and make the time as big as possible, which would be 0.64 over 1/2, I'm sorry, no A in here, my mistake, just 1/2 T squared. Now, if you want A small, you want T big, so put T as big as possible up here or down here, 0.64 squared. And you're going to get a number here. You can do the same thing for A max. And then you look at how far off are you? How far off is this from, what is the range here? A max and A min. So A max, you would have your biggest possible D here, which is 2.15, minus, this one is now you want the smallest VI, which is negative 1.2 times, and you want the, let's see here, we're going to make this as big as possible. So we actually want the big time here, 0.64. Oop, sorry, you're getting in the way. Over 1/2. You want the smallest time down here, 0.54 squared. And so I'm just going to run these numbers for you. You could run these numbers. It's not a hard thing to do. Let's see, the 1.2 times 0.64 equals, we'll make that now, plus minus, plus 2.05 times 2. That's the same thing divided by half, divided by 0.64 squared equals. Okay, the minimum possible acceleration I'm getting here is 6.3 about meters per second squared. The maximum acceleration I'm getting here. So this one, we're kind of avoiding the percent error game. We're just going to see, does it fit? Well, let's try. 1.2 times 0.64 plus 2.15, that's that minus negative, times 2 divided by 0.54 squared equals, oh my goodness, 20. Maybe I did something wrong with the math. Did I do something wrong? 1.2 times 0.64 plus 2.15. That numerator is just much bigger. Divided by, yeah, this can be right, 0.54. Yeah, 20. So based on our error, the possible range of answers here is anywhere from 6.3 to 20 meters per second squared. With that in mind, our answer of 8.7 has quite the uncertainty range, and we could actually claim, okay, well, you know what? We are okay here. We're okay. The trouble here, however, is this is such a big range that you might then say, we need to do a better job. Because if all of these answers are possible, well, then I can't really trust my 8.7 that much. And we need to squeeze down on our uncertainty. So I'm going to put a little math model on how to do this next. It's kind of an add-on. And for those of you who like running numbers in a fancier way, you could check that out. But for now, here you go.